Hello, we're going to be working on section 10.2 answer check, and I'm going to go through some of the problems with you. And to do that, I'll be working with a whiteboard. I will also show you the answers and tell you the answers to questions within the problem set. So section 10.2 is working with conversions. So you have to remember your factor label method and use it, of going from moles to mass and moles to volume at STP. And those are important relationships that we need to use conversions for. We'll start by just reminding you that you should have already learned about a mole, which is a quantity, 6.02 times 10 to the 23rd of anything is a mole of that substance. We use that value for chemistry because it allows us to work with amounts of atoms or molecules that we can measure, that we can work with. So this concept of a mole is really important. And in our mole to mass relationship and mole to volume relationships, we're going to be using a couple of things that we work with as conversion factors. The first is the molar mass, which is the number of grams that we have if we have 1 mole of a substance. And that molar mass is found on our most important reference page, which is the periodic table. So for example, if I wanted to know the molar mass for helium, I would look at the periodic table under helium and look for the value that we know is the same as the number of AMUs for an average AMU for an atom of helium. That's the same value that is the number of grams if we had 1 mole of atoms of helium. So helium here, it's got a molar mass of 4.0, and that is the number of grams that we'd have of helium if we had 1 mole of helium. So the first problems that I'm going to work with are the sample problems, 16 and 17. So remember that when you work through these, it's always important to read and look at the analysis that introduces the problems. So problems 16 and 17, if you look above, it kind of walks you through the process, and I'm going to do that as well. The process is determined, or sorry, in this case, by what is being asked. So the question here for number 16 is where to find the mass in grams. So we're looking for how many grams we have of C20H42. Sorry, that looks like an O. If what we have is 4.52 times 10 to the minus third moles of C20H22, sorry, 42. The little note that we have in our book here says we need to just start by determining the molar mass of the compound. So that's a really important piece here. We want to know how many grams there are if we have 1 mole of C20H22. Well, in 1 mole of C20H22, we would have 20, the equivalent to 20 moles of carbon. So we're going to take 20 times the molar mass of carbon. Where do we find the molar mass of carbon? We look on the periodic table. So carbon has a molar mass of 12.0. So we're going to take 20 times 12.0, and that's in grams per mole. So we can do this in our head, but we can also work with a calculator. So 20 times 12, and I can put in the 0.0, not that it matters, gives us 240.0 grams per mole for just the carbon part of this compound. We're going to add to that 42 times the molar mass of hydrogen, which hydrogen has a molar mass of 1.0 grams per mole. And that will give us 42.0 grams per mole. We're going to add those two together, and I'll talk about the significant figures for that. So that looks like we have 282.0 grams per mole. Whenever you're working with molar mass from the periodic table, all of those values on the periodic table have significant figures, values that go to 1/10 of a gram per mole. So we should always, whenever we have a molar mass, that molar mass needs to be shown to the 1/10 of a gram per mole. So we're adding those together for a total value. So that's our molar mass for C20H22. Now we're going to use that in a conversion for this problem. I'm going to work over here. This is number 16 still. Now, when we do these problems, just like with the conversion problems we worked with before, the first thing we want to do is write the given value and units. So that is this value. I'm going to do that above. So for number 16, the given value is 4.52 times 10 to the -3rd moles, and that's moles of C20H22. Now I'm going to multiply that using factor label method by the value that I have, that I can calculated here, of 282.0 grams equal 1 mole. Okay, so we know that if 282 grams equals 1 mole, we need that 1 mole on the bottom here, so it'll cancel with this, and 282.0 grams go on the top. Moles will cancel. Then we plug those values into our calculator. Remember, 4.52, if we want to take that to the -3rd, we use EXP, not times 10, and then -3 times 282.0 equals. And I get a value with lots and lots of sig figs. So I'm going to write that value down. And then we'll adjust for sig figs. So just a reminder on this, we have 3 sig figs here. And we have 4 sig figs here. Since we're multiplying these together, our solution needs to have the same as the least number of sig figs of anything that's been multiplied or divided, and that would be 3. So I'm going to adjust this to 3 sig figs, which means it will be, this will be our last place. The 4 does not round that up, so it's 1.27, and that is going to be grams. Those are the units that we are left in, and that's C20H42. Okay. So again, when we're solving for the number of grams given moles, we use the molar mass with an orientation that allows for moles to cancel, and we end up in values of grams, C20H22. Now, just to check, this is not a very large mass, but given that we had much less than a mole, okay, 0.00452, if we take that out of scientific notation, we could see that we wouldn't have a very large mass, because if we had 1 mole, we'd have this amount, but we have way, way less than that, 0.00452 of that, so this makes sense. All right, so that was sample problem number 16. And now I'm going to show you and read through the answers to the rest of the sample problems for that section, those 2 pages. I'll show you the answers and point out some of the things that we need to keep in mind as we work these. Now I worked number 16, and the solution is 1.27 grams C2H42. For number 17, the solution is 225 grams FeOH2. I'd like to work with this problem just briefly in order to show how to find the molar mass, which you were required to do in order to solve this problem correctly. So one of the things that we need to realize is how many of each we have. We have 1 iron. So we look on the periodic table and get the value for that iron, 55.8 grams per mole. And we know that the 2 that we have here means we have 2 of these OHs. So there are a couple of ways we can work with this. We can find the overall molar mass for oxygen plus hydrogen and then take that times 2, or we can say we have 2 oxygens and we have 2 hydrogens. Either way will work. I'm going to say we have 2 oxygens. So 2 times, we look on our periodic table, that's 16.0 equals 32.0 grams per mole for the oxygens, and then 2 times 1.0, which is 2.0 grams per mole for the hydrogen. When we add these together, 8 here, a 9, and an 8, we get 89.8 grams per mole. So that would be the value you would have used to solve for this. So make sure you're correctly coming up with the values for the molar masses. Remember, that's the amount of grams per mole that we have for a substance, and then using it correctly in the factor label method. Okay, if you're not sure how to do the factor label method, you can look back at the information on the sample problems or go back earlier in this video where I explained how to work with that. Number 18 on the next page, we were solving for moles of this substance, boron, and you could have 0.0343 moles of boron, or you can have that in scientific notation, 3.43 times 10 to the minus 2 minus second moles of boron. Number 19, the value is 0.987 moles of N2O3. The next piece that we're going to look at is looking at molar volume at STP. And there's a very specific volume if we have 1 mole of a gas at standard temperature and pressure conditions. The standard temperature and pressure conditions are very specific, and we're talking about gases in this case. So standard temperature is 0 degrees C, and standard pressure is either 1 atmosphere or 101.3 kilopascals. At STP, when we have 1 mole of a sample of gas, which is 6.02 times 10 to the 23rd particles, that is going to have a very specific volume of 22.4 liters. That 1 mole equals 22.4 liters can be used for conversions, and we can use it either with the moles on the bottom to cancel and the liters on the top, or we can use it with the mole on the top and the liters on the bottom. So we're looking for using this when we have samples of a gas at STP. So again, if we are working with calculations, remember in your book, they have information that helps you to determine how to work through problems of this type. That's what this part of the sample problem set is working toward. And then you have some problems that you work with this same method that you're going to use to practice. Okay. In this case, for example, for the first problem for number 20, it says, what is the volume of these gases at STP? So STP, gases at STP, we know will have a volume, if you have 1 mole, of 22.4 liters. We're going to use that for a conversion. The first one says, if we have 3.20 times 10 to the minus 3rd moles of CO2, what is the volume at STP? So I'm going to work through that on the whiteboard. This is question number 20. And we have 3.20 times 10 to the minus 3rd moles of CO2. And we want to know how many liters that is at STP. So the first thing that we want to do is we want to write our given value with units. And set up our factor label grid. Now let's determine what is going to get us from moles to liters at STP. And we know that that value is 22.4 liters equals 1 mole of a gas at STP. Let's look at how we would use that in this conversion. Well, the 1 mole we know needs to go on the bottom to allow us to convert from moles, and the liters on the top to allow us to get to liters. So 1 mole goes on the bottom, and 22.4 liters, which is the volume of 1 mole of gas at STP, goes on the top. That cancels our moles, and we end up in units of liters. So again, we work with our calculator. 3.20. Remember, EXP is the key, and then minus third. We're going to take that times 22.4, and that gives us this value in the calculator, 7168. Now we need to look for significant figures. Just a reminder, in a value that's in scientific notation, the first factor, this part, is going to tell us the number of significant figures for this. Remember that righty zeros are significant if they are to the right of non-zeros and there's a decimal in place. So this is 3 sig figs, and this is also 3 sig figs. That means this needs to be adjusted for 3 sig figs. These lefty zeros are not significant. So this is the last place for significance. We need to look to the right of that, and the 8 will round that up. So our value here will be 0.0717, and our units are liters. Let's double check and see that is what we were trying to solve for. So that is liters of CO2 at STP. Just a note, if you are starting with liters and you want to know number of moles, this conversion factor would be flipped, okay? So if we had a value that was working with liters converted to moles, we would write our value in liters. We'd have our conversion factor with liters on the bottom, 22.4 liters on the bottom, 1 mole on the top, and we would work the conversion that way. Here's the answer check for the sample problems. I'll start with number 20, and then I'll do an example from 21. So previously I had worked through number 20. There is your solution. You could show it either in scientific notation or not in scientific notation. For problem B, the answer is 82.9 liters of N2. For problem 3, 21.5 liters of CH4. Now let's look at problem number 21, where we're working in the opposite direction. So we can see here that at STP, the problem says we want to know how many moles are in these volumes of gases. So we're going to do 21A, which says we have 67.2 liters of SO2. .2 liters of SO2 equals how many moles at STP? And again, that at STP tells us that we have information about the number of liters per mole. In fact, we can show here what our conversion is going to have to include, which is that 22.4 liters equals 1 mole at STP. To work this problem, again, to start, I'll write the given value and units, set up my factor label grid, and then with this equivalence, because these equal each other, then I can use those to change the units and the value for how we describe this SO2. Because liters are what we need to cancel, and they're in the numerator here, we need them into the denominator in our conversion. So 22.4 liters here equals 1 mole. The 1 mole goes on top. Liters will cancel, and we're going to end up in units of mole. Again, with our calculator, 67.2. We're going to now divide that by 22.4. And we get a value of 3. So this is a little bit different for our significant figures work because the calculator answer has actually fewer sig figs than what we need in our solution. So let's look at these values. This 67.2 has 3 sig figs. 22.4 also has 3 sig figs. That means our solution needs to be written with 3 sig figs. And it still needs to have the value of 3 units, 3 one place. So in order to do that, I add a decimal and 2 zeros. That's still a value that indicates this relationship, but now I'm showing it correctly with 3 sig figs. The units, of course, are moles. That's what's being asked for, and that's what we've solved for, the units that are left, and that's moles of SO2. So the reason I wanted to show you this one is we can use this 22.4 liters with the liters on the top and moles on the bottom, or liters on the bottom and moles on the top. Same with our molar mass values when we're converting from grams to moles. So that gets us to our answer check for number 21. As I said, 21A, 3.00 moles of SO2 at STP. B, the solution is 0.0393 moles of helium, or you could write that in scientific notation, 3.93 times 10 to the minus second moles of helium at STP. And C, 44.6 moles of C2H6. The next piece that we want to look at is working with density. In your book, they describe using molar mass and density and working with the values that give us density. Remember, density is when we have a mass divided by a volume. And when we're working with density, those units, depending on what the substance is, might be described in grams per milliliter, or grams per centimeter cube, or maybe kilograms per liter. These are, or kilograms per kiloliter, these are mass divided by volume terms. Now, if what we're working with is actually a gas, because gases have very little mass per unit volume, we tend to use values of, say, grams per liter instead of grams per milliliter when we're referring to gases. For gases at STP, in order to solve for density, we can work with a density value that is the molar mass divided by the molar volume at STP. And I'll show you how that works in terms of our values. Our molar mass has values that are grams per mole for a substance. Our molar volume, we know, is in values of 22.4 liters equal 1 mole at STP. So let's say, for example, we have helium, which if we look on the periodic table, we know that that has a value of 4.0 grams per mole. And of course, if it's at STP, we have 22.4 liters for 1 mole. In order to find the value of density in grams per liter, we can see that the moles cancel, per moles cancel with per moles, and we could solve for this value and get a value in grams per liter for helium at STP. All we need to do is take our 4.0 divided by 22.4. And that would give us a value, if we need 2 sig figs, of 0.18 grams per liter, which is the density for helium at STP. So you could solve for the value for any gas at STP if you know its molar mass, and at STP we know that we'll have 22.4 liters per 1 mole. Working with that information about density and molar mass and molar volume, let's look at our sample problems 22 and 23. So for sample problem 22, it says we have a gaseous compound composed of sulfur and oxygen that has a particular density of 3.58 grams per liter at STP. So this is the density that was given, right, of this sample or this substance. We want to know what the molar mass is, and the hint here tells us we can use the density and the molar volume of a gas at STP to get our molar mass. So just a clue, the units actually can lead us here. A molar mass, we know, is going to have units of grams per mole. So to set this up, we want the liters to cancel so that we'll end up in units of grams per mole. So I set up the 22.4 liters with the liters on the top and 1 mole on the bottom. And we run our math. 3.58 times 22.4 gives us a value of 0.192 grams per mole. For this substance, now the calculator answer, we check our sig figs, 3 here, 3 here. So keeping these 3 sig figs is correct. For problem number 23, when it asks what is the density of krypton gas at STP, we have a hint here that says to do problem 23, first find the molar mass of krypton. So we're going to look on our periodic table. Krypton is a noble gas, and it has a molar mass of 83.8 grams per mole. And then it says use the molar mass and the molar volume at STP to calculate the density at STP. So to start this problem, I wrote down the molar mass of krypton, and I want to use the molar volume to get to a density. Now remember, molar volume at STP is 22.4 liters equals 1 mole. We want density, which will be in grams per liter. So we can see that to set this up so that moles cancel from top to bottom, we need the 1 mole on the top and 22.4 liters on the bottom. When the moles cancel, we'll end up in value units of grams per liter, which is a mass per unit volume, which is a density. So to solve for this, then, we plug into our calculator, 83.8, and we divide it by the 22.4 and get to a calculator answer of 3.74107. Okay, let's look at sig figs. 3 sig figs for this, 3 sig figs for this. So we need the significant figures to end here. 3.74 grams per liter is our answer for number 23.
Good morning, LHS. Begun to arrive in the bus loop, so if you're taking the bus home, go on and head on down. Thank you and have a great weekend.
All right. For our lesson check, we're going to look at the number 24 through 31. And for this, I'm going to read off the question, and then I will also read the answer. Okay. All right, number 24, how do you convert between a mass and the number of moles of a substance? You need to use the molar mass, which is in grams per mole, and we get that value from the periodic table. Number 25, how do you convert between the volume of a gas at STP and the number of moles of a gas? We use the molar volume at STP, which we know is 22.4 liters equals 1 mole at STP. Number 26, how many grams are in 5.66 moles of CaCO3? You need to use the factor label method in order to get to this value. So you're going to start with moles, use the molar mass of CaCO3, which you calculate using the values on the periodic table. And then in that calculation, you should get 567 grams of CaCO3. Number 27, find the number of moles of 508 grams of ethanol, C2H6O. So you need to find the molar mass of ethanol and then use that in factor label method to get to the value for the number of moles of C2H6O. which is 11.0 moles C2H6O. Number 28, what is the volume in liters of 1.50 moles of Cl2 at STP? Now, this is sometimes throws students because if we are working with moles at STP and we want a volume, we don't have to find the molar mass of chlorine. All we need to go from moles to volume at STP is that 22.4 liters equals 1 mole. So set up your factor label method, and your answer for number 28 should be 33.6 liters of Cl2. Number 29, 3 balloons filled with 3 different gaseous compounds, each have a volume of 22.4 liters at STP. You should recognize that, okay? Do these balloons have the same mass or contain the same number of molecules? Well, they will likely not have the same mass unless they have the same molar mass. If it's helium and you have that 22.4 liter volume, you have 1 mole of helium, which has a mass of 4.0. But if what you have is hydrogen, H2, it would have a mass of 2.0. However, each of them would contain the same number of molecules, okay? Because they would all have a mole of molecules. Next, number 30, the density of an elemental gas is 1.7824 grams per liter at STP. What is the molar mass of the element? Well, in order to solve for that, you would take this density and multiply it times 22.4 liters over 1 mole, and you would get to a molar mass of 39.9 grams per mole. For number 31, we have gases A, B, and C that are at STP and have these different densities. Calculate the molar mass of each of the substances and identify each substance as ammonia, NH3, sulfur dioxide, SO2, chlorine, Cl2, or nitrogen, N2, or methane, CH4, okay? So in order to do this, we would solve for the densities of the 3 substances using those starting densities. So for number 31, I'm going to work through this. Substance A had a density of 1.25 grams per liter. And we want to know its molar mass by using 22.4 liters divided by 1 mole at STP. And we get a value of 28.0 grams per mole. Okay. For B, same thing, 2.86 grams per liter times the 22.4 liters per mole at STP gives us a value of 64.1 grams per mole. And for substance C, we have that 0.714 grams per liter. Take that times 22.4 liters per 1 mole, and we get a value of 16.0 grams per mole. Now, these molar masses can be used to help us identify what the substance is. Okay, so the possible substances, as listed in the book, get that out here. The possible substances that this could be include NH3, SO2, Cl2, N2. Okay, so we're going to write those down. NH3, which is ammonia, SO2, Cl2, N2, and CH4. Now, if we find and solve for the molar mass of each of these different substances, then we can compare to the molar masses of A, B, and C. So using our periodic table, we're going to add together the 14.0 for 1 nitrogen and 3 times 1.0 for the 3 hydrogens. So 3.0, we get 17.0 grams per mole as the molar mass for NH3. While we're working with nitrogen, let's go to N2. This would be 2 times 14.0, which gives us 28.0 grams per mole for N2. SO2, we look for sulfur, 32.1, plus 2 times the mass of oxygen. So oxygen, each oxygen atom is 16.0. So we're going to take that times 2, which gives us 32.0 plus the other 32 is 64.1 grams per mole for SO2. Cl2, we take 2 times the mass of chlorine, which is 35.5. So 2 times 35.5 gives us 71.0 grams per mole for Cl2. And then the last one, methane, carbon, is a 12.0 grams per mole. We add to that 4 times hydrogen's 1.0. So 4 times 1.0 gives us 4.0. So that is 16.0 grams per mole. Once we found the molar mass of all 5 possible compounds, we're going to look at and compare those to A, B, and C. So A has a mass of 28.0 grams. We can see that that is then seems to be N2. B has a mass of 64.1 grams per mole, and that would match up with SO2. And then for C, that has a mass of 16.0 grams per mole, and that matches the methane CH4. That concludes our video for 10.2, answer check and problem types. If you have any questions, please email your teacher or talk to your teacher during class or another time during the school day.